Okay, let's get going. So welcome to this crazy week. If you didn't have lab yesterday, you will have lab tomorrow. And if there are conflicts still, like you had some meeting that didn't get canceled or whatever, try to go online and change. But actually, you don't even need to really this week. Don't worry about that. If you need to go to a different lab tomorrow, go to a lab that you need to go, that you can go to. Preferably bring a laptop because there may not be enough space, and we'll try to fit you in. Okay? Let's see. I think that's it for the big stuff. So here's what we're going to do today. I'm going to do a Unix tip of the day on. It's actually one that you may or may not use, but some people have asked about how to copy files from their laptop, let's say, to the file server. We're going to talk about that. Then I'm going to have a couple comments on late work. You guys I hopefully saw my email that I sent out I guess it was Friday, saying, hey, stop submitting stuff late. And I apologize if that was a little terse, but some people were still submitting stuff after deadline. I'll comment on that. And somebody pointed out in an an actual email that I didn't have any late policy on the website, right? Which I actually still don't, but I'll put something on there. But we'll talk about that too. Then we're going to talk about testing your code. So as you guys found out from homework 2, the tests that we gave you in the main.cpp to start out with were certainly not exhaustive. And then once you got to providing, you saw all these other error messages because something went wrong with your code. Well, I'm going to teach you today a little bit more about how to do some of those tests yourself so that in the future when you provide, that won't be an issue. Okay, you really do have to write your own tests a lot of times. And then finally, we're going to talk about this new data structure called a tree, which I gather you guys at least saw something about in Comp 11. So this will there'll be a little bit of review, but we'll go into a lot more nomenclature than you would have seen in Comp 11. So we'll get to there. Okay, that's that. Let's see. The Unix. Does anybody have any questions on that before I start? No? OK. The Unix tip of the day. So here's what I wanted to talk about. SCP and CP. CP is just copy. So if you want to copy files from point A in your file structure to point B, you're going to use the CP function. You could also use this function called SCP, which actually works perfectly well without being between servers. But it was primarily designed as what's called secure copy, which will use SFTP or the SSH technology to actually copy your files securely from your laptop to the server or back and forth. And I'll show you how to use that. Okay? All right. Let's say that I am in my folder here, which is not showing up. Hang on. I'll do this. Whoops. Come on. Whoop. There we go. All right. So I am in my folder here, and I've got a whole bunch of files. Let's say that I want to copy this file called main-with-tests.cpp into some other folder in my computer. Right? It's really easy to do. And we've done this for the labs, like copying, right? CP, and then main-with-tests, and then where it's going to go. So I've actually, in this case, if I do the little tilde sign right here, that's the little squiggly if you can't see it. That means your home directory. That's the shorthand for your home directory, right? And so that will be a little tilde. And if I do slash, and then I happen to have a folder called downloads, this says copy main-with-tests.cpp into my home folder, downloads folder, like that, right? And boom, it goes in there. Okay, and then if I looked in downloads, it would be there. It's pretty easy stuff. If you want to copy from your own laptop, like mine right here, to the homework server, for instance, okay, you can use SCP, and the format is exactly the same. SCP main-with-tests.cpp, and then you need to put your username and where you're trying to send the file, right? So SCP main-with-tests.cpp, this is me, cgreg@homework.cs.tufts.edu. Then you put a colon after it, right? You put a colon after it, and then the file structure from your home directory where you want to put it. So in my home directory, I happen to have a TMP, temporary files, folder. So if I did this, and I said SCP main-with-tests, cgreg, homework at tufts.edu, cs.tufts.edu:temp, and then I don't know if you have to, but I generally put a little slash in there that says put it in the temp folder. And if I do that, it will connect through the system and then tell you exactly how much data it's transferred, 100%, how big it transferred, and how fast it was. Right? Now, there wasn't much to transfer, so it really wasn't that fast. But it will do that. A lot of times it will ask for your password. I happen to have a passwordless login set up, so it's using a private key on my computer to like check and make sure I'm really who I say I am. So you don't need that, but a lot of times it'll ask for your password. So that's it. It's the same exact format, and you can do that. If you want to copy multiple files, let's say I had a whole bunch of .h and .cpp files, scp star.h star.cpp makefile, right? That will copy all those files, anything that's anything.h, anything.cpp, and my makefile, and then I do the same thing. C Greg at Tufts or homework, blah, blah, blah. Right? Same exact thing. Question?
Is the default location that the temp folder, is that inside of your user?
Yes, so we'll get into this a little bit later in class actually, but when you log on, you start out at whatever your username is. So I start out at cgreg, right, /. So it's like /h/cgreg is where cgreg, right? That's where I start out. So yeah, wherever that colon is, that's like right here. And that's where the next one would be your desktop, right? And some people did like comp 15, et cetera, on there. So you start right there, yeah. Yep. If you tried to do it back here, it wouldn't actually let you. But it's because of the permissions and so forth. But that's where it goes. Okay. Questions on copying? A slightly better idea for many people is just to download a GUI-based file copy program that I like. What's the one I use? Well, I have a couple different ones that I use. What's the one that's the duck? CyberDuck. You can't see it down at the bottom of my screen. It's a little duck. I actually just keep it because I like the icon. That's really the only reason. Anyway, so that's how you do copying files. So if you need to copy files from anything, if you happen to be using a PC and you want to do a terminal, there are ways of doing that. I think Putty is one, and Sigwin is another. There's some other ways to do that. Okay? Questions on that? All right. All right. OK, comments on late work. So this email that I sent, I kind of was like, stop providing. If you haven't provided, or if you provided late, I'm going to give you a 0. Blah blah blah. I am not in the business of wanting to give people zeros, right? Like that's not my thing. If you provide a few hours late, I'm really not going to care. Okay? I mean, I put the deadline at midnight for a reason, right? I mean, I kind of want you guys to like have a goal in mind so that maybe you get some sleep or whatever, right? And if you are late, I'm not going to be too concerned. Nobody's sitting up at 12:01 going, oh, who's provided, right? Nobody really cares. So I don't care if you're going to provide late, and I'm not going to just cut it off. All right? But if you're going to be like a day late, or like the next day, if you're going to be like, I can't get it done tonight, I'm just going to need to start fresh tomorrow morning, email me and we'll work it out, right? I mean, the people that I emailed and talked to, I don't think I denied anybody an extension. I mean, I might have said, look, you can have 1 day, depending on circumstances, or 2 or 3 or whatever. But that's the bottom line. So I did not mean to scare anybody into thinking that if they provided a few minutes late, they're going to get a 0 on this. Okay, but please do let me know. That's about all I have to say. Any other questions on that stuff? And I'll try to put something on the website to that effect. Thanks for the emails about that. If you happen to be in here, thanks for the emails about that. OK. All right. So let's go into talking about testing your code a little bit. As I said, you go to provide, and all of a sudden Bruce has 1,000 tests, and your programs fail some of those tests, and you go, oh, I didn't even think about that, or I don't even know what that test means, right? Well, today I'm going to show you a relatively easy way of doing tests. Now, people who are in 15 or Comp 50, you guys had a way easier way to do tests. Like in the programming language they use, this Dr. Racket programming language, it's very easy to do tests, and it highlights your code when things don't get tested and all this stuff. It's kind of cool. We don't really have that available to us. But I will show you a way that it will be easier to actually provide, or to make these tests so that you can go through piece by piece and do it. And you really should think about setting up those tests right after you write a piece of code. Right? You write a piece of code, and you say, I better write a little test for it. That's kind of the right mentality to think about. You kind of have to begin writing your own tests. And we're only going to give you, if we give you any tests, they're going to be very, relatively small tests. We're not going to test all your stuff. And that's that. Questions before I show you what we're going to how to do that sort of thing? OK. Here's what I'm going to do. Let's take a look at, let's see, where did it go? Here we go. So one of your classmates, who will remain nameless, actually, I'll do this with a bigger screen. And I hope I anonymized this properly. This is the output from his or her tests. OK, this is what they got during provide. And I wanted to show you what it is. I'm kind of going backwards here because you won't necessarily have provide in order to write your tests. But you should be thinking about the kinds of tests that we do. And now that you've seen this one, you can say, oh, maybe I needed to think about that sort of thing. But anyway, so the test goes through. It does the simple tests that we gave you. It actually tests those, and the advanced ones as well. This person did great on those. And then it tests the event functions. Great, great, great. No worries. Emma before works. Print works. Setters works. By the way, you want to test, if you're going to do tests, you want to test kind of the minimum that, how should I put it? Not the minimum, but the functions that are going to get called all the time first, right? Like your getters or your setters. Let's say your setter screwed up. Let's say you said event start time equals event finish time of some, whatever, when you were doing your setter, or return event finish time when you meant start time, right? Well, that would mess up probably every other thing you write in your entire rest of your program, right? So if you don't test that, now you don't always have to write a specific test for that. I mean, if it's a one-liner or whatever, eyeball it and make sure. But just so you know, if you're finding really weird errors, and you're like, I've checked everything, just go back another step and check something else. But anyway, this person did great on these. Great, 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 terrific there, terrific, 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 blah, 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 blah. Oh, here we go. OK. So this person's code, this person failed a test that says same times. OK, and all this like shorthand here is Bruce's way of saying what's going on. You're basically setting an element. You're creating a new day, and then you're let's see, creating an event, and then you are setting the event. You're scheduling the event in the event list, and then you're printing the day, and you're scheduling another one. You're printing the day, scheduling another one, blah blah blah, right? And notice, in this case, all of these events are the same time with the start time. OK, so that's what this is. It says same times. OK, in the handout, when we said that we had events that had the same start times, what was the answer? What was supposed to happen in your program? Yeah. The one that was there first took precedence. I mean, it was supposed to be before it in the list. The one that's already there should stay there in its place, and the other one should go after it. So your event should go after all the other events that are the same time, start time, in there. OK, so this person, obviously something went wrong with that. OK, so let's build a little test for that. Here's what I have done. I have, here we go. This font is huge. OK, I have taken this person's main function, and I've just stripped everything out of it. Right? The main function does nothing now. It just returns. OK? Here's what I want to do. I'm not going to actually type all this stuff, but I'm going to show you. I'm going to copy paste some of it, and then we're going to go through some of it. OK? Here's what you might want to do. OK? If you're going to do a test, all right, the first thing you might want to do is start out a little section in comments that says, look, I'm starting my test. And by the way, you can do this in main.cpp if you want. It doesn't really matter to me. In fact, we won't ever check your main.cpp for being the same as what we gave you. So you can do what you want in there. All right? You could also make another file that has functions in it. If you want to make a different function for every test, that's fine too. I'm going to show you a relatively easy way here. OK? So you could write a little comment here. This wraps around because of the font's way too big. But here's what you might write. Look, I'm starting the tests. I'm going to test for scheduling events that are at the same time. Check. Then maybe you want to say what the test is going to do. The test will schedule two events on the day that start at the same time but have different descriptions. And it doesn't even really need different descriptions, but whatever. That's what you're going to do. You're going to do. OK. Then you might want to write something like, what should happen? Right? The second event should be placed after the first event. If you can't write what should happen, then you obviously don't understand what you're trying to do. Right? I mean, you should be able to write what should happen in your code. And if you don't understand it, come to office hours. We'll figure it out. Right? Or put something on Piazza and say, I don't get what this is supposed to do. All right. And then Here, then I might do this. I might say, this is what I'm going to do. I'm going to schedule an event. I'm going to schedule the first event, which is at 0900 to 1000, called first event. Then I'm going to also schedule 900 to 1000, called second event. And then I'm going to print the day. Right? That's fair enough. What I might do after that is, and this can be a little tricky too, right? This can be a little tricky, but put what you expect. Here's what I expect. I expect it to say start time 900, end time 1000, description first event. Start time 900, end time 1000, description second event. That actually tells you, hey, I'm done. And by the way, this is so far, this is all comments. Like, we haven't done any code yet. This is just all like what this test is supposed to do. Okay? All right. And that's just important so that you can figure out what, in the end, what you've actually done. So here's what I might do next. I might say print out. I might actually print out. OK? Well, I might say, look, here's what I'm testing, scheduling them at the same time. Print that out to the screen. Then I might say, here's what I expect for the output. And I like to put these little dashes here to say, hey, this is where to be able to figure out where you're looking. Start time, blah, blah, blah. This is exactly what I expect. OK? And then this is the rest of what I expect. All right? And then I put a little divider to say, hey, that's the end of what I expect. Okay? This is the first part of the actual code, but it's just printing out right now. Then I might say something like actual output, right? I might say, here, this is what I'm actually looking for, the actual output. And then after that is where I have to write my code to actually do that. Right? So here's what we might do. I'll put all this stuff, and then we'll go through it. All right, here's what I'm going to do. I'm going to create a day, right? A new day. It's a pointer to a day. Then I'm going to create two events with the same start time and different descriptions, like I said I was. Event 1, first event, event 2, second event, they both start at the same time. Okay. And then I'm going to actually schedule them. Schedule event 1, schedule event 2. And then I'm going to print it out, exactly what I said I was going to do. Okay. Why did I create a day pointer and not just a day? It doesn't really matter in this case. I think we're going to be using pointers later for days anyway. If we have a list of days, it's probably easier to do a pointer for it anyway. So that's why you could have done it the other way. I don't think it really matters in this case. Okay? These would have been periods instead of pointers and so forth. OK, so now we've got what we expect. Well, put a little divider that says, here's when my output ended. Okay? And by the way, this is all just you can do it this way. You can do it your own way too, but I'm just showing you the way I might do it. And then, OK, so in Bruce's scripts, Bruce has these cool scripts that actually tell you whether or not your output is correct or not. We could do that. In fact, if we use the event CSV function, that gives you a string that you can then compare against your output. Pretty cool. In this case, I'm just going to do it like by hand, in other words, or in some sense. I'm going to say, look, here's a string. I'm going to print out, is this what you expected? Yes or no. If you type yes, then you say the test passed. If you type no, and then the test failed. Pretty simple. All right? And then I'm going to say I'm done testing that event. And then you do have to do a little cleanup, delete the day if you nude it, et cetera. And then end of scheduling tests on the same test. OK? So that's the first one that I'm going to do. Now, what is all this other stuff here? Hold on. Oh, that's this. There we go. I forgot to copy it. OK? So I'm going to copy. I'm going to print all that out. And it's going to say whether to test. All right, are we done? We ready to test it? I think so. Let's see if it works. OK, build succeeded. Here's what the test looks like. OK, let's see if I can get this bigger screen. No, hang on, maybe this. There we go. All right, so here's what it did. It said, scheduling events, doing my test, expected outputs here, right? Actual output is here. OK, let's see. Hold on. I'm wondering if this is actually the correct output. Actually, looks like it is. I thought I had the person's code copied over. Hold on a sec. Let's see. Calendar dynamic array. That looks right. Worked great earlier. Hold on. Day dynamic array. OK, so Let's see. Checks to see if there's enough capacity. If there's no place in the array. First position checks the event before, moves events over. Checks the events at the same time. Checks if the events are at the same time. Puts the second event after the first event. OK, so this is actually, maybe I am doing the wrong one. Hold on. Not actually sure what's going on. Why it's doing the, it looks like it's running the wrong code. Hold on. Nope, that's not it. Dynamic array, check, check. Did we get the right output? No. We did actually, didn't we? So somehow it miraculously healed itself. Hold on. Let's see. Dynamic array, I just want to make sure that it's, well, hang on. Let me stop task, cancel out, try again. All right. Now you're getting a feel for what the morning class gets all the time. Just kidding. Well, not really, unfortunately. All right, hold on. Window. I don't know why it's actually not giving me this. OK. So, I don't know why it's not doing this. There we go. All right, there's that, and there's that. And if I do this and this, it's still not showing me. This is the one we just did. Schedule the events, failed. OK, that's that. Hang on. All right, I'm about to give up on this in 1 second. Calendar dynamic array. Try it again. Run. End of actual output. Yes. Must be thinking it's the wrong file. How about this? Anybody use Xcode before? You can actually do this cool thing where you do, if I can find it here, product clean, where it actually rebuilds everything. Stop. Clean succeeded. Let's see. Ah, there we go. OK, that was what it was. It hadn't actually recompiled after I copied. So here's what came out. The second event did not print. OK, this is the person's original code. Second event did not print. Well, what do? We go check in that event, and or the scheduling, because we know where it is. We just checked for the schedule event, and this person was actually pretty nice to us. Here she said, a space that said, checks to see if events are at the same time. Oh, nice. OK. And then they do this whole business. And this is hard to read because the font's the wrong size. But what they said was, if temp gets start time equals event list I, start time check, sounds good enough. Begin event capacity -2. You start to have red flags when you see stuff like that. If you are doing something where you're moving one element or moving another element, and all of a sudden you're doing 2 away from something or 3 away from something and like hard coding that in, you know you're probably in trouble, right? So this is kind of getting ugly, and we could look through this, but then we kind of realize. Remember what we said about 2 events. If event A and event B are at the same time, is event A before event B? No, it's not, right? So your am I before function actually will return false for those 2 events. If you coded it right, it turns out that you don't even need this whole part about checks to see if events are at the same time, blah, 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 right? Turns out you don't even need this now. Let me see if that's actually where I needed to delete it there. I think it is. All right, let's see if that compiles now. It did. Let's try to run it again. Let's do it this way. Try to run it again, and ta-da, that did it. OK, so now that actually works. So it turns out that person actually did more work, and it was wrong, which is too bad. But that's the way it goes. OK, let me show you another example. OK, let's go back to the report again. So we had this one failed, and then some other things come in here. Let's see, we'll go down to where it started. OK, scheduled duplicates, also not OK. OK, if you went and wrote a test that checked duplicates, the only real difference between the test for that and the test we just did was that it's going to check and see if the end time and the description are different, right? Turns out for this person's program, we actually that fixed the program. So we won't try to test this one, but you might want to anyway in your own code. But let's go down and see what the next one is. Aha! Cancel single. OK, so if you have something in your, if you have an event in your day, and it's the only one, and then you cancel it, OK, that might be a corner case, because it's the only one, and your day has to end up with 0 events and so forth. Let's check that. OK, let's see how we might check that. OK, the easiest way to do it is to go back to our main, right, and to say, I'm just going to copy the entire test from the last one. Now, if you're doing it in a function, same thing. I mean, you copy the function and do everything, just copy paste in this case. To make tests like this, it's not that time intensive. Okay, somebody emailed me and said, hey, you didn't give us a way to make these tests. Well, I did. It's right here, right? I just didn't show you how, which is probably the issue. OK, so here we go. So this time, what are we going to do? We're going to cancel one event. Test for canceling one event. OK, what's the test going to do? It's going to schedule an event and cancel it. OK? All right, done. OK, what should happen? Well, the event should be canceled. Right? All right, so what's our test going to be? Well, we're not going to actually schedule 2 events. We're just going to schedule one event. Let's call it the event. OK? So we're going to schedule that event. Then we're going to print the day again. In fact, this time, let me print out the CSV file, right, which is going to be export CSV. That's what we're going to do in this case. Then we're going to cancel the event. Cancel the same event. And then we are going to export CSV again. And then hopefully those two, the second one won't actually have the event because we canceled it. All right. Well, what are we going to expect this time? OK, we're actually going to just expect the CSV. Now, if you remember, the CSV looked like this. If we started 0900, it would be 09, or I guess it would just be 900, and then 1000, and then the event. And then we're going to have some blank space, right? And then it's just going to be nothing left. Like nothing else should print out, because the second time we export CSV, it should not be there. OK, everybody with me so far? All right. So then we go down here and we say, OK, look, change this. Cancel an event. Expected output. Well, we already said the output was going to be 900, 1000, and then the event. OK. And we can get rid of all this other stuff because it's not even necessary. OK, the actual output. Now, the actual output, so there's going to be some errors here, actually, as it turns out, because you have to change a couple things. OK, so let's just do that. We already created a day. You want to redo your day. This is another reason we want to do it. We want to redo a new day because we don't want that old data possibly interfering with our new thing and messing our tests up. In other words, the other data might still be there. So we always want to recreate our objects if we can. OK? Now, I guess we're doing it more or less the same way here. Event 1 is going to be like this, and it's going to be the event. And then we are going to schedule the first event. And then we're going to print out the day. Now, in this case, it's actually, we're going to have to do it this way because we get a string. Cout a day, export day like that. OK? And then we are going to, maybe I spelled it wrong. There we go. Export day. And then we're going to cancel it. A day, cancel event. And it's going to be event 1. And then we're going to print it out again. A day. Sorry, I'm using an IDE, which tries to fill in stuff. It's really annoying. Export day. All right. And that's it. And then this other stuff is all going to be the same, except for can't. Did I do it again? Cancel single event. Thank you. Same thing. I can't type. And down here, we actually already created a string, so we're just going to set it equal to nothing for right now. And then we're going to ask for our input again, and blah, blah, blah. OK? Pretty simple. I wrote that second test in about, 4 minutes. Right? OK, let's try it. So here's what's going to happen. We're going to rerun this, and it is going to say, let's see, hang on. right, navigator, there we go. It's going to say, this is our first test still, by the way. So our first test did pass, passed, okay? Test passed. And then the second one here. All right, it's going to cancel an event. Expected output, 0900 the event, and that's it. Actual output, 900, 1000 the event, and then garbage. Ugh. Okay, so that person has garbage. So no, this didn't pass the test. All right, well, let's go look in the person's, let's see, it's going to be in the cancel event, because we just tested the cancel event. So let's go check. Okay, dynamic array. Let's see, schedule event, schedule event, schedule event, schedule event, cancel event. All right, now let's see if this person did it right. I don't expect you guys to necessarily be able to like comprehend all this fast, but here's what the person tried to do. Okay, go from 0 to event count. This one's fine. If event list I is same as an event, okay, that's what we're trying to do, right? We're trying to find the same event because we're canceling it. Check. All right. For int j equals I, j is less than event capacity j plus plus. So what they're doing is they're saying, go up until we find the event, start there, and do something from then on. Okay, all the way up to, looks like event capacity. Then they say event list j equals event list j plus 1. Sorry, the font's too big, but maybe I can do this. Just move it over like this a little. There we go. All right. So then they said, oops, event list j equals event list j plus 1. All right. Then they do this. They set the start time. They reset the event, and then they exit. OK, what was this person's problem? Any ideas? I'll let you think about it for a second, and then I'll answer. I'll let you guys answer. A couple people have their hands up. A couple people, OK. What do you have? You had the hand first. Or maybe you did.
They're doing the opposite of canceling it, where they're like stopping at like the event they want to cancel, and then just shifting all the events next to it like over one, so that there'll be like an open space.
Are you sure? I'm not sure that's exactly what they're doing. It looks like they're doing this. They're taking the event at j and moving the j plus 1 event into that one. That's actually legitimate.
But then they're just leaving like an empty spot, and they're probably going to hit the end.
They're leaving an empty spot. What, you mean at the end they're leaving a spot?
No, like right at the event.
Oh, I don't think so. I think they actually do this part. This part, actually, I think they do correct. You're a good idea, but I think they do it correct, where they say at that part, move everybody else forward one. I think they do that part correct. I may be wrong, but I think they do. So, but good idea. Yeah, if you had a few more minutes, you were to. Sorry, you had your hand up next, and then, yeah. What'd you have? Yeah.
Oh, I think she forgot to event count.
So there's no decrementing event count, is there? That's definitely something. Is that what you guys were saying? OK, there's maybe, but that's definitely one of them. Let's do that. Let's do it right here. Event count minus minus. OK, that's one of them. Yes, Suzanne.
She essentially like creates another event that lasts for the entire day down an event minus.
This part?
Yeah, at the end of the list.
Yeah, the event count minus 1. Well, I think he or she's just trying to actually just zero it out, which is actually not necessary, as it turns out. I don't think that's going to cause a problem. It might be unnecessary, but I don't think that's going to cause a problem. Yeah. Good idea. Oh, well, now it will. Oh, all right, hold on. Let me. All right, it wouldn't have before, but let's actually just get rid of this stuff here. How's that? We don't even need it. We don't even need to reset the event. All right, now would it work in that case? All right, so what else is wrong? Anybody else? Yeah. Yeah, take a look at this. First of all, okay, they go all the way up to event capacity. Right? Is the event capacity where our events stop? No, that's the event count, right? But you may have brought up a very good point. See this little j plus 1 here? That little j plus 1, it's going to go all the way up to, in this case, event capacity. And it's going to go to that end, event capacity, which is in like 5, let's say. And it's going to go 5 and try to put 6 into 5's location. Does 6 even exist? We may not have memory for that. Some other variable might be using it. We're not even allowed to touch it. Okay, it's called a buffer overflow or an array overflow, right? So that's that's what's actually going to cause the crash. And if you look back at the code, it actually crashed on the other test that it did. So definitely like that. And then finally, this is wasting space. Yeah, you were going to say?
I think there's two loops. And the first loop is like you actually canceling like a lot of events, right? Let's say.
Oh, you might cancel more events than one. Yeah. Now, this test that we're doing wouldn't necessarily catch that, right? How would we stop that?
Just break.
Break, yeah. Break or return or whatever. But yeah. Yeah, Dylan?
So the way that two things. One, we got rid of the plus ones. Now it looks like we're not doing anything in our second form.
Yeah.
Where did I do it? Did I do it wrong in the wrong place? Oh, you're right. You're right. Sorry, you were right. You're right. This one's going to be +1, but what is going to change? It's not going to be event count. It's going to be what? Nope, not this one. Sorry, this one.
Oh, well, you changed. Yeah.
Yeah. How about that? Would that work?
Well then.
Wouldn't it be event count minus?
Then you do a special case for the last.
See, I got.
I'm not even sure you need a special case for the last one because your event count's going to go down by 1. So who cares about moving that last, the one that you're canceling? So let's try this with our event. Okay, this may not be exhaustive, but let's try this. So we've made a whole bunch of changes. This person, oops, didn't do quite so well on this event cancel part. Okay, but let's just try it and see what happens. Get rid of that. Get rid of that. And there we go. Okay, so the first event was still fine. Second event, let's see. Expected output. So it's supposed to be this, and then actual event, and then nothing. Yep. So it's just supposed to be that, and that's it, and same thing. So that actually did work for our test. Now there may be other tests for canceling events. You should probably test canceling multiple events, canceling event at the end, canceling event at the front, sort of thing. Okay. Yeah. But anyway, did you see how relatively quickly we were able to A, test our own knowledge of what's going on, B, test the code itself. Once we write one test, we can copy paste a lot to write multiple tests. And it actually is not that time intensive. And you'll find a ton of bugs that way. Okay? So try to do this sort of thing for the next couple of assignments. Next week in lab, we're actually going to do a fun assignment, fun lab where we give you tests to find bugs in, and you'll have to write some test code and so forth. So it'll be kind of fun. All right. Questions on testing? No? Awesome. OK. Let's see. 4:15, right? Yeah. I want to make sure I'm on track. OK. All right. So as I said before, you guys, those of you in 50, did you guys do trees at all? You did? Lots of trees. OK. All right, good. Well, this will be a little bit of a review. If you want me to go faster, say speed up. This is too slow. Well, don't do that. But we'll go relatively quickly in this stuff. All right. So you guys are going to be experts at trees. So if you know what trees are already, look, trees, linear access time for linked lists, not so great. We've talked about this a number of times. We've said if you want to walk through a linked list to get to some event way at the end, it takes a while, right? It takes on the order of however many events are in the list, on average half that, but on the order of however many events are in the list to get to that last event. Not such a great strategy. Different, more or less the same for an array in the sense that if you don't know the index you're going to, you still have to walk through and search for things in an array. Okay? We can do better than that. All right? We're going to come up with this thing called a tree, which you guys have already seen before, turns out. We're going to discuss why it's so good at the access time, probably next week, or maybe tomorrow, but definitely next week. And let me show you exactly what some of the details about trees are. We're going to look at a couple things with trees too. So your file structure in your Linux file system is tree-based, or tree-like anyway. It may not be the underlying data structure may not actually be a tree, because there's other ones that tend to be faster for what they're trying to do with directory structures. But in other words, you can model a directory structure very easily with a tree. Okay? We can also evaluate arithmetic expressions with trees, kind of like what we did with stacks. Okay? It actually looks somewhat similar. And then we can get really fast searching with trees. It's amazing how fast you can search through trees because of the way they're set up. It's all about more information. On the first day of class, I said, look, there's this idea of providing more and more information to you in your data structure that allows you to do things quicker and more efficiently. Well, this is one of them. And then finally, we'll take a look at these things called sets and maps. We won't get to that today, but we'll get to that eventually. Okay. Questions so far? All right. The notes are online. By the way, all the code is online too. Somebody emailed me and said, hey, can you put the code online before class? Well, I've started to do that, so hopefully I'll continue to do that. OK. So what's a tree? A tree is just a collection of nodes, much like a linked list. All right. You can have an empty list or an empty tree, which has no nodes in it. If you do have a tree that's got nodes in it, the first node, kind of like the head in a linked list, is called the root. Okay, it's called the root. And the root we can call R. And the root has either 0 or more non-empty subtrees. So a tree can have a subtree, can have a subtree, can have a subtree. Okay, this is that whole idea of recursion that we talk about all the time. Well, trees are perfect examples of why recursion is really helpful. Okay, because you've got the same structure underneath the current structure. And then you've got all these other subtrees whose roots are connected by what we call an edge from the root. Okay, so the root will have edges, and edges are just lines, as it turns out, when we draw them. Okay, and that's what you'll end up seeing in the tree itself. Okay? Pictures are worth 1,000 words here. I get your picture on not this slide. Yes, this slide. That was the next one. Okay, here's a tree. All right, so take a look at this tree. A we call the root, right? B, C, D, E, F, and G are all attached directly to the root. Okay, we'll get to what they're called in 1 second. Okay, H is connected to D below it, et cetera, right? And you'll see the structure. Okay, it's just the same. This is the structure of trees in general. Okay, the trees that we like to deal with don't really look like this. Okay, but I'll show you an example of. We'll get to the ones that we do like in a few minutes, called binary trees. Okay, but this is the tree. It's got a root, lots of nodes that connect to the root via these edges. Okay. We call B the child. There's a lot of nomenclature. There's definitely a lot of nomenclature for trees. And they go back and forth between using like actual tree metaphors, like root versus the root of a tree, although this is like an upside down tree if this is the root, right? Trees from the sky or something, right? But anyway, you've got the root, and then they go from that metaphor, and then they go to this like family tree metaphor, right? So they talk about B being a child of A, right? And A being a parent of B. And same thing here. F is a child of A and a parent to K, L, and M. All right? Now, notice something about this. There are n nodes, A all the way through P. OK, so there's P nodes in this case, right? But in this case, all the way to P. And there's n minus 1 edges. Why? Because everybody has one parent, and the root does not have any parents. Check. N minus 1 edges in all trees. Okay, go prove it to yourself if you want. All right. Nodes with no children, we call them leaves. Okay, why do we call them leaves? It's back to this tree metaphor, right? They're kind of like the end of the tree, right? They're the leaves on the end of the tree. So all these ones in red are the leaves. Okay. Nodes with the same parent, back to the family tree metaphor, we call siblings, right? So B, C, D, E, F, and G are all siblings, right? H has no siblings, only child. I and J, siblings, etc. Good? All right. What we do is we define paths from a parent to its children. We generally don't define paths across branches. We generally define paths, as you can, but we generally define paths from a parent to children. Okay, so for instance, A, E, J, O is a path, right? And the length of this path is the number of edges. 1, 2, 3. How far, or in other words, think of it this way. A goes to P. How many jumps does it take? 1, 2, 3 jumps. Or A to O. 3 jumps. Right? We're not going to worry about going backwards this way. If we wanted to go A to M, it would be 1, 2. 2 jumps is the length from A to M. Okay, the path. All right. We then have the depth of a tree. The depth of a node is the length from the root. In other words, how deep is it from the root? It's pretty simple, right? O has a depth of 1, 2, 3, right? J has a depth of 2, 1, 2. It's kind of similar to the path in that from the root, right? In fact, it's the same. But the depth of a node is how many jumps it takes to get from the root. Then we've got the height, which is kind of going the other way. It's like how high is it from the bottommost node? Okay, the height is the longest path from the node to a leaf. So you go from, let's say, well, in this case, we used the height of f, right? F to its farthest leaf down is 1. Okay? Well, it's in its sub-branch, and that's in that sense. Okay? The height of f, 1. Okay? The height of all leaves is 0. So height of these guys, 0, 0, 0, 0, 0, 0. Okay? A's height, right? You have to go all the way to the lowest one that it can get to. So that's going to be 1, 2, 3. The height of A is going to be 3. Questions on that? Okay. All right. Lots of nomenclature, like I said. All right. The height of the tree, well, as I just said, that is the height of the root. In this case, the height of the tree is 3. 1, 2, 3. Nodes, back to the family tree again, have ancestors and descendants, right? E is what? It's an ancestor of P, because P comes later down in the tree, right? K is a descendant of F. K is also a descendant of A. K is not a descendant of E, because you can't get down to K from E, right? They're like somewhat related, but they're not descendants and ancestors. All right. Let's see. Did I miss any? I think I talked about parents and children, right? You can also have grandparents and grandchildren. You could probably have cousins or whatever if you wanted to. But like the grandparent of J is A, right? This is kind of like that little case where the person was doing +2 and -2. If you're ever dealing with grandchildren, stop for a second and say, is this really what I want to do? Because it's 2 removed, and there might be a better way of just being 1 removed from the actual solution. Okay? All right. That's it for the nomenclature. Questions on the nomenclature? Getting some people looking like, oh, we're bored, or looking like, oh, I don't, something's wrong. Everything all right? All right. OK. So another question is, how do you actually implement a tree, right? Well, we're going to have to implement this. We already said that it's a linked structure, not a linked list necessarily, because it's just a linked structure. We could have a node to each, we could have each node linked to each child, right? So the root in this case was like A through G or something, right? We could have A linked to B, linked to C, linked to D, linked to E, linked to F, and linked to G, and somehow put that in a struct, right? You could do that. The problem is, when you create a tree, do you know how many children any node is going to have in a generic tree? You don't, right? You have no idea. You also don't know how many, and it could be lots. I mean, A could have 1,000,000 different children. You can't just keep direct links to A for 1,000,000 nodes. You wouldn't be able to build a structure that does that in code. It just doesn't. It's hard to do, or really hard to do. Okay. So what we can do is this. This is going to look really odd. Okay. Maybe you've seen this before, but this is an odd. I don't really like it so much because it's asymmetrical, and I like symmetry. So it's not particularly symmetrical. But look at how we could do this. We could say that a tree node has some element, like in this case A, and then it has its first child. Points to its first child, and it also points to its next sibling. So take a look at what this tree is. This is the exact same tree as I had back here. Let me refresh your memory what this one looks like. A's children are E, F, and G. E's children are I and J. A's first child is E. E's next sibling is F. Does that mean that it's a child of A? It does. And then F's next sibling is G. Anything sideways on this chart is a sibling. Anything down is a child. Okay, that's why it's asymmetrical. I don't really like it that much. But what it allows you to do is you don't have to know how many children there are beforehand. All you need to know is you're going to have 0 or more children, and you're going to have 0 or more siblings. And you can have a linked list or an array or whatever you want to do the siblings, right? So E might have a linked list that goes to F and then F goes to G, right? It's kind of like a linked list. Yes?
Couldn't you run like a dynamic array of pointers?
Could you? Sure. You could have a dynamic. Yeah. You mean to do E to F to G?
No, to keep it symmetrical. So have A have a dynamic array of pointers to E, F, and G, and if you want to add a sibling, you just add a pointer into the array.
Sure. You could do that. You could have A be a dynamic list of pointers to E, F, and G if you wanted to. Sure. Yeah. But then you've got pointers to dynamic list of pointers to dynamic list of pointers. I mean, either way, it's another abstraction. You could do that. Yeah. Good call. Yes.
Is there supposed to be a connection between I and J and O and P?
So let's look at the other one. Let's just look over here. So I has a sibling of J, and J has a child of O, and a sibling of no other siblings. J has a child of O, right? And O has a sibling, which is P. So let's go back and look. I has a sibling of J.
No, I just couldn't see the line.
Oh, sorry. Yeah, there is one. Right there, you mean. Yeah. Sorry. OK. Other questions? Yes?
I'm sorry, can you go over like the difference between height and depth?
Sure. Difference between height and depth. OK. The depth is how far you are from the root. Think about going down underwater.
Right.
Right? OK, so the depth of I, 1, 2 hops from the top. That's how deep it is.
Okay.
OK? The height is the longest path from the node to a leaf. So however you can get to the leaf and the longest path there, that's your height. So the height of A, getting to a leaf this way is only 2 hops. Getting this way is 2 hops. Getting this is 1, 2, 3 hops. Therefore, the height of the root is 3.
Okay.
Okay? Good. Question?
Any other type of tree, does it matter which child comes first?
Yeah, good question. The question was, does it matter which child comes first in this type of tree because it's a sibling sort of thing? Depends if you're sorting it or not. I mean, if you want it to keep it sorted, yeah, sure it does. If you don't, no, it doesn't matter. You could have A's first child being F, and then F's siblings being E and G, and it doesn't matter if we're not keeping it sorted in that sense. Yeah, yeah. We just have a relationship between parents and siblings. OK. So we kind of get this kind of ugly but an asymmetrical way of describing trees in this case. It works. I mean, it works. Null links. By the way, we don't draw any null links. Null links would be all over the place. I mean, if you had to draw one there, and there, and there, and there. You wouldn't want to do all that, right? No, don't do all well, I forgot going sideways. But anyway, don't do all the null links. Just leave them blank. Just know that they are null. They don't point to anything. Well, they point to null. Okay? Any other questions on the basic stuff here so far? Yes, Dylan.
Does it take a computer a lot of time to navigate from one pointer to another?
Does it take a lot of time to navigate from one pointer to the other? Yeah. I mean, it's not that fast, but it's fast enough. I mean, in the degenerate case, this ends up being one long linked list.
Yeah.
That's the degenerate case. I mean, not much you can do about it if you end up that way. There's ways of balancing trees, which we will talk about, where you can keep it so that nothing ever goes all the way down a list for a long way. But yeah, good question. Link traversal is not that slow. It's creating each node, which takes a little time. So there's trade-offs to this. But in general, trees are generally fast. In general, they're generally fast. Yeah. In general, they're fast. OK. Other questions on the basics of this stuff? Yes.
So something like N's first child would be null.
N has 2 null links. It's got first child null link and next sibling null. Both are null in this case. Yep. Good. Anything else? All right. OK. So let's look at a file system. OK. So your file system, as you guys have realized already, when you type cd to get to a new directory, right, you're basically traversing this system of directories which have files in them. Some of those files could also be directories which go to other directories and files, et cetera, all the way down. Right? In this case, I'm marking all the directories with a little asterisk. So A is the root of the directory. If you go to the homework server or whatever, right, that's the / directory, which is slash, and then maybe you have like G, which is all the users, and then slash, and then your username, right? Like that, and then that's what so this is the root, and then this is the next tree, the next node, and then this is a directory, a node under that, and they're all directories in this case. Okay? And then we have files as well. The files have both a size, and the files and directories also have a size, right? Somehow you have to keep the information about the directory, what the name is, right? What its next pointers are and whatever. So that takes some amount of space. So we'll just say that directories have a size of 1. Okay? So if you look at this, A is the root. A's children are E, F, and G, and et cetera. It's the exact same picture as we did before. Okay? How these are children, because this is the siblings, et cetera. Okay? We can do this. We can actually list all the files, and guess what? We're going to do it recursively. Woohoo! We can also find the sizes recursively. Okay? It's not quite as pretty as you might like, but it's not too bad. Okay? Let me show you a little bit of code on that. All right. So here's the kind of the first picture here. I know it seems like a lot of code. It's not too bad. Here's what I'm going to call a directory entry. It's going to have a file size. It's going to be a Boolean to say whether or not it's a directory. True would be a directory. And it's going to have some name. That's going to be a directory entry. Then we're going to have a tree node. Okay? Tree node is just a structure that holds directory entries and our first child and our next sibling, just like what we had before. Okay? That's going to be our overall structure of the file system here. Okay? If we want to print out the file system, when you print out a file system, here's what we're going to try to do. Okay? We're going to print the root, and then we're going to print for all the files and directories under the root. We're going to like tab over, right? So maybe we're going to have directory 1 and file 1 and file 2 or whatever, right? Okay, let's say there's another directory, and it would be directory 2, and then it would have like file 1a and then file 2, etc. We're going to try to do this so that it prints nicely. Why not? Right? Here's how we're going to do it. Okay? It's going to be a recursive idea, and it does get a little bit ugly because of the fact that we've got these sibling things, but we'll work through it. We've got our base case. If node is null, we've got to get out of there, return. We then print the node. We print the name, and we print it when we pass along the depth. I'll show you the print method in about 1 minute. Okay, but we're going to print it. We're going to say what node we're printing and how deep it is. And we're going to start out at the root and a depth of 0, because that's how deep the root is. OK, if it is a directory, here's where we need to print all the files under the directory. Okay? So if it's a directory, we need to print all the files under the directory. So we're going to list all, which is what we're doing here, list all the first child at a depth plus 1. So why is depth plus 1? Because our children are 1 more depth than us. This is where it gets a little ugly. Then we say, all right, look, let's create a temporary node, which is the first child next sibling. Like I said before, this is where it gets a little bit hairy, because now we're dealing with like grandchildren here, right? So be careful. It's not really grandchildren. It's actually children, but it seems like it because there's 2 pointers. But remember, we're just getting the next child. In other words, the directories and files under the directory. And this is how we have to do it for this model. Okay, and then I'm just going to go through all the rest of the children and say, list all of that children at that depth, because it's a child. List all the siblings, and then temp node equals temp node next sibling. So I'm going to walk down the list of siblings. And then I'm going to be done. Questions on it? Just a recursive call and then another while loop in there thrown in because it's kind of ugly. Okay, here's what the print file name print name looks like. We loop through from 0 to depth, and we print tabs. Aha, that's where our depth comes in. So remember, the root's going to have no tabs. It's at 0. Directory 1 is going to have 1 tab because it's 1 down. Directory 2, or the files under directory 2 are going to have 2 tabs, boom, boom, because they're 2 in. So we loop through that. We then print the actual name. If it's a directory, I'm going to print a little asterisk to tell you it's a directory. Why not? And then we're done. Pretty simple print method. Questions on that? No, if you have them, sorry. Okay. Here's what it looks like when you actually do this to the same tree that we did before. Okay. Prints the root. I should have had it print A. Prints A, it's a directory. Prints E, which is the next directory. Prints E's files, I and J. J is a directory, so it prints its files, O and P. Then it goes and prints F, which is the next child of the root here, and then K, L, and M, where it's its files. And then G, and its file. Okay, and it looks nice. Nice little like indented list, and you can see exactly what it looks like. All right. Any questions on that? Okay. Yeah.
So F is a sibling of E, even though it's another directory within E? Or is
F is a sibling of E. So take a look at look at this picture. It's slightly easier to understand. Root has how many different files in it? 1, 2, 3. They all happen to be directories. Okay? And so yeah, so E and F are siblings, but they're both also directories. Yeah. It's like the G folder. All the folders in here are other directories for all you guys and me. Good? All right, this one isn't too bad. We can also print the file sizes. This is more code. I'm not gonna blast you with it too much right now, but it's basically the same idea, right? You're gonna count up the size. You're gonna get the total size, which is your size, plus, if you're a directory, get the size of everything below you, all your children, right? Well, you get your first child, and then you also get all of the siblings, which are also your children, which is exactly the same methodology as before. And you just add them all up, and you add the total size each time. This one's recursive, this one's a loop, and then you return total size. Check. Okay. Pretty simple stuff. And you return total size. And here you return total size. If it's only a file, you can return total size. If you didn't care, if you only wanted the size of the whole file system, you could actually do this much cleaner. You could just recurse through. You could say total size equals size first child plus size of the next sibling, and you go all the way down and do it. But because we want to be able to say what's the file size of just this file, we have to do a little bit of extra work in there. Go look at the code online if you want to. Okay? All right. So enough about all those funky looking asymmetric tree structures. Right? Let's get back down to the basics here. There is a special kind of tree. Why is it a special kind of tree? Because it is called a binary tree. Binary being 2, it only has 2 or fewer nodes. Okay? The nodes we call left and right, which kind of makes sense. Right? This one's to the left, this one's to the right. And you can have 0, or you can have 1, or you can have 2. So A has 2 nodes, left and right. B only has a left. D has no nodes, no children. Right? So its lefts and rights are null. And E and F are the same. The leaves in a binary tree always have no nodes. Well, they always do in general. Okay? That's what a binary. And then the structure. Because it's a binary node, we know how many total nodes it could have. So we might as well just say, let's just connect them directly to our node. Each node gets a left and a right, and then we're done. No more of this like first child, first sibling, blah, blah, blah. We don't need to worry about that, which is great because we don't want to. We don't like those kind of trees too much. Okay. Questions on that? Binary trees? Okay. Binary trees have a little bit of an issue, right? First of all, they have good qualities. They do have very good qualities. The first quality is that the depth of the average binary tree is generally less than the depth of not less than the number of nodes, which means it's better than a linked list. If you want to get to, let's go back a sec. If you want to get to F, what's the maximum amount of jumps you have to do if you're at the root? 2, right? Same thing for any of the things here, only 2. All right? That happens to be a logarithmic amount, but in terms of the amount in general. But as far as the average goes, the average amount is actually the square root of the number of nodes. If you take all binary trees, and we're not sorting them or anything like, or making them kind of any more special than just regular binary trees, the average depth is like the square root of n, which is great. You get that much more efficiency just by doing a binary tree. However, it can devolve into this degenerate case, which is just a linked list, right? Because let's say there nobody has left nodes. A only has a right, B has a right, C has a right, D has a right. This is just a linked list. All right? So it can be as bad as a linked list, but it could also be very, very good. Okay? Trade-offs. Okay? We like the fact that it can many times be very good. Yeah?
Since you don't, let's say you're looking for a certain node F, if you don't know initially whether or not it's going to be on the left side of the root or on the right side, don't you still have to search through all of the nodes?
You do. The question was, if you don't know if it's going to be on the left or the right, do you still have to search through all the nodes on average? You do. That's why we have different kinds of binary trees that give more information. And the binary trees that have more information are the ones we really like, because then you can absolutely determine which side it's going to be on, and then it's very fast to search. Good. Good question, though. Yeah, in general, the searching isn't going to benefit you too much in this case, because if it's just a binary tree. Yeah. OK. All right. So this is actually where I'm going to stop, but I'm going to show you this, and then we're not going to actually do it. Remember the other day we did stacks, and remember we said stacks are you can push items onto a stack and pop them off a stack, and you can do these arithmetic expressions, right? You can do additions and subtractions and all that. Take a look at this. Can we figure out what this tree is representing? Yeah.
You wrap each subtree in parentheses.
Yeah, let's try it. Let's actually write down what this actually means in our regular old math functions, right? Okay, so where do you want to start? Let's start at the plus right in the middle. Right? Start at the root. Right? We're going to have some parenthesized something or other there, right? And we're going to go over this in more detail tomorrow. But if we do that, then we're going to say there's another plus over here on the left-hand side here, because we're going to add this to this, all right? Whatever this is getting added to this. That's what that means. Add the two children. So we're going to add this. Well, let's look at this one. This one has a plus, right? It's got a plus that we'll put like right here. And that's going to have some parentheses in it like that, right? And so the plus there is going to have parentheses. Well, what's on the left? Ah, that's nice. It's just an A. And what's on the right? Well, it's a times. So that's going to have some parentheses. And what's on the left of that? B and then C. Right? So far, so good? That's this side. Let's go to the other side. Well, what do we have? We have a times over here. I'll actually put it here because I can kind of see what's going on. OK, and we're going to have parenthesize that. OK, so let's see. That times is going to have, on the right, it's going to be just a G. On the left, it's going to be a plus. So we'll do that here. Plus, and that's going to be parenthesized. And then it's going to be plussing something over here, and then F. So F. And then this one is times. So it's going to be like that. And we might need another parenthesis there. And it's going to be timesing D and E, multiplying D and E. D and E. All right. So now this is what you might call an overly parenthesized expression, right? There's like way too many parentheses there for what we're used to. And incidentally, we talked about this last week. The whole PEMDAS thing, like the order of operations. Why do we have order of operations? So that we can get rid of a lot of these parentheses, right? Where don't you need them? You don't need them here. You don't need them here. Let's see. We do need them here. But in other words, you can get rid of a lot of parentheses by having these order of operations that we all decide are the right ones. You ever remember in like your first algebra class where your teacher's like, what is this going to mean? And like she writes out a whole list of things, and you have to, like, everybody in the class has a different answer because nobody knows the order of operations, right? Well, that's why we put them in there, so that we all have to agree on them. Or we all have to overly parenthesize everything, right? But anyway, we can look at these trees, and the trees will actually help us do this kind of format. And we can also maybe do other kinds of formats as well. For instance, if we wanted to, let's see, if we wanted to always go left, A, and then go back up here and go left, B, and then go back, and then go let's see, right when we get to here, C times plus. Does this remind anybody of anything? A, B, C times plus. Does that remind you of maybe postfix notation? Right? A, B, C times plus, right? You do B and C times, then you do plus that thing with A. You can get that from this tree as well. We'll go through that tomorrow as well. Any questions at this point on trees, binary trees, other kinds of trees? Anything else? All right, then I'll see you guys tomorrow.